Okay, so the next method of finding the volume of revolution, or the volume of a solid region of area revolved around the x-axis, called the washer method. And it's called the washer method because instead of having, when you slice perpendicularly to the x-axis, instead of having a solid circle, you're going to have a hole in the middle. Okay, so it can occur with more than just area between two curves, but this is all you're responsible for the semester exam, so I'm just going to focus on this, and then we'll talk about other things that you use HLYs for your IB exam. Okay, so for right now, you're just going to need this when they ask you to find the area between two curves. It's a very simple formula. So here I give you two curves, y equals to x squared and y equals to root x, and I graph them out, and as you can see, where these two intersect here and here, there's some area in between them. Okay, now I'm calling this f and g, you can call this g and f, whatever. Okay, they're just functions, and they're two different functions, and so, you know, I'm just giving them different names is all. Okay, so the first thing you want to do is you want to make a little sketch, right? And the square root of x, or the square root of anything, is pretty much going to be bigger than x squared. So, you know, if I had a 2x in here or a 3x or whatever, it's still going to be higher than x squared. And why am I saying that? You'll see in a second. So the first thing is you make a sketch. Now we need to find the limits of integration, okay, for our integral from a to b. And to do that, you just set the two functions equal to each other and solve. So I did that down here. I said x squared is equal to root x, squared both sides to get rid of the radical, brought everything over to the left, set it equal to 0, factor and solve. So my limits of integration are 0 and 1. So what I know so far is that I've got an integral with 0 and 1. I don't know anything else yet, but I have that. Now, if I spin this thing, right, so I'm spinning it around the x-axis, I get this other little leaf looking thing here. What I notice is when I cut vertically or perpendicular to the x-axis, I'm going to have this hole, everything where I cut here is going to be a hole, and I'm just going to get these little bits of area. And if you look on that, or if you look at that head on, what you're going to see is something like this. That's called an annulus. So when you revolve this thing, what you're going to get is this bowl looking thing that's actually a very thin shell. Okay, you could put cereal in it or something. Just think of a cereal bowl. Okay, and we want to find the volume of the bowl part. Okay, not the empty part inside. So the formula for an annulus is pi times big radius squared minus little radius squared. Now it's important never ever to switch these in your integral. Do not switch them, because again, a lot of times on the exams they'll just ask you to choose the correct integral, you know, A, B, C, or D. And if you swap those around, they're gonna do it on purpose, you're going to get the wrong answer. So do not switch them. It's big radius minus little radius. Well, what's big radius? Remember that the radius of a solid or volume of revolution goes from the axis of rotation to the curve. Well, now we have two curves. So the big radius goes from the axis of rotation to the curve furthest away from it. So my big R is this function root x. Okay? My big R is the function root x. And the little radius is going to go from the axis of rotation to the curve closest to it. So my little r is the function x squared. So I wrote that down over here to the side. Okay. So my area formula is pi times big radius squared minus little radius squared. And if I clean that up, I get this right here. This is what I need to integrate. Okay, in that order. So we say volume is equal to pi, the integral from 0 to 1. Big radius minus little radius, or top function minus bottom function, okay, dx. And if I integrate, you know, that's easy, x squared over 2, x to the 5th over 5. I've got to evaluate it from 0 to 1. And so if I plug the upper bound in, I get a half minus a 5th here, minus, if I plug the lower, I get 0 minus 0. So I know this has been happening a lot, but it's rare. It happens equally likely that this could be a 2 or a 5 or some other number, and so you're going to have to compute this and then subtract that from that, so you're going to have to be careful with the arithmetic. But anyway, if I clean this up, I get 3 over 10 times pi, so 3/10 pi. Now if you get to use the calculator, that's really nice, because you're going to have two parts to your exam, And, you know, I don't know if you're, I mean, you're definitely going to have a volume on there, but I don't know if it's going to be on the calculator or non-calculator part. So you need to know how to do it by hand, right? Number 1, find the limit, make a sketch. Number 2, find the limits of integration. Number 3, determine what your area function is. It's pi times big R minus little r if it's two curves that intersect. And then 4, integrate that, okay? But anyway, if you get to use your calculator, it's really cool because, well, let me do this first. The original functions were x squared and root x. So if I put those in, because they're two different functions, and I graph them, you're going to get the same picture, just a little nicer, more accurate than the one I drew, right? And this area here is what we're going to rotate around this x-axis. Now if I do a second calc 7 from 0 to 1, what it's going to do, remember, second calc 7 computes the area between the curve and the x-axis only. So you see, I'm not getting any of the area that I need, okay? Not at all. Now I could compute the area under root x and then compute the area under x squared and then subtract them, and that's just too much work. Rather than that, once you figure out your big R and your little r, just put it into your calculator like that. X minus x to the 4th. And hit the graph key. There's big function minus little function, or top function minus bottom function, okay? And then do second calc 7 from 0 to 1 using the limits of integration that you found, and you see the area is 0.3. Now remember, I got to multiply this by pi, so if I just do times pi, it'll take me to the home screen. I'll get 0.942. Now if I put in my 3/10 pi like I did from the one I did by hand, it's 3 pi divided by 10. You notice I get the same exact value. So I did it correctly by hand. In my calculator, if I put in, again, so remember, I got to put it into the area function first and then just put big R minus little r, hit the graph key, and then second calc 7 from A to B, whatever your interval is, and it'll shade it, and then multiply that result by pi, and that'll give you the answer. Let's see, here's another one from number 9 in the book. So in number 9, the picture's there, and they give you x squared and x cubed, and I chose this picture for a reason. I always use this one when I teach this, because kids think that the curve x cubed is bigger than x squared, and it is for the most part, but not over small intervals, it's not. So I wanted to use this, okay? So the picture's there, so you know, I just copied it down, and the pink curve represents x squared. So from 0 to 1, so this is 1 here. My pen doesn't want to write. There. From 0 to 1, x squared takes on larger values. After 1, x cubed will take on larger values. So that's important to know. Now, if I do second calc intersect, or if I set them equal to each other and solve, I get 0 to 1. So I know that the area is contained between the two curves on the interval from 0 to 1. Those are my limits of integration. I also know if I spin this thing around the x-axis, right, I'm going to have this, so again, something like this. I'm going to have this hole in the middle, so I need this formula, right? So it's pi times big radius squared minus little radius squared. So big radius again goes from axis of rotation to the curve furthest away from it. Little radius goes from axis of rotation to the curve closest to it. So in this case, that's what it is. And if I clean it up, that's what I get. So that's exactly what I need to integrate, right? Pi from 0 to 1 of that thing. And I did it by hand again, because most of them you can do by hand. Anyway, I get x to the 5th minus x to the 7 over 7, evaluated from 0 to 1. We're going to have 7 minus 5 is 2 over 35 times pi, so 2 pi over 35 cubic units, because again, this is volume. And that's what we need to do. Okay, so just study these couple examples for right now. We'll go more in depth when we return from the break. You're not going to need to know more than this for the semester exam, and I'm just trying to do a little bit of house cleaning or housekeeping of little things since I've been out. Okay, Let me know if you have any questions.